Hello, my name is Michael Hall, and today I'm going to be explaining Coulomb's law. So, Coulomb's law is defined as F equals K, absolute value Q1, Q2 over R squared. So, what this value tells us is the amount of force that is between two charges at a certain distance from each other. So it's their interaction. So the forces they experience. So, really quick, the first thing I want to talk about are the variables. So F is going to be the force, that's what we're finding. K is a constant, and we'll talk about that in a second. Q is going to be the value, the amount of charge those two charges hold, and then R is going to be the distance between those two charges. K is a constant, and we'll write that value up right now. So K is going to be equal to 8.99 times 10 to the 9th newtons meters squared over Coulomb squared. So, you need to remember when you're using this equation, there's a couple of things actually. First off is going to be units. So, remember force we always want to end in newtons. Forces are always measured in newtons. We're saying those are equal to K, which is newtons meters squared over Coulomb squared, times by the charges, which will be coulombs for both of those, and then radius, which should be measured in meters, so meters squared. And we should cancel out to newtons, which we do. So coulombs cancel, meters cancel, and we get newtons on both sides. So that's what we're aiming for. Make sure that you are using coulombs and meters whenever you're calculating this. Okay, the other thing that we need to remember is because this is an absolute value, we're always going to come up with a positive number. There's no negatives in here. K will always be positive. The charges, whether they're positive or negative, will end up positive because of the absolute values, and distance will never be negative. So our force is always going to be given to us in a magnitude. So the way that you tell which direction that force is going to be applied is based on negatives versus positives. So you need to remember that opposites always attract. So if I have a negative charge here and a positive charge here, whatever the force is, I know that the force will be pulling them together. Alright? Whereas, actually, throw this up there, if they're the same, so if I have a negative and a negative, we know that those forces will be pushing them apart. Now in most cases, in the problems you'll be solving, one of these charges will be fixed. So you know that all the force will be on the other one. So this one can't move, so all the force has to be on this other one. Okay, so that being said, we're going to go ahead and give a couple of example problems a try. If we have, we'll do 3 today, we'll start with number 1. If we have a positive charge of 2 times 10 to the negative 4th coulombs, and say we have a negative charge over here, we're going to say this one is fixed, this one can't move. And this negative charge is going to have a charge of 3 times 10 to the negative 4th coulombs. And we'll put them at a distance of 5 meters. Nice round number. So if we plug these numbers into our equation, we're going to get K, well, we'll just write the actual value up there. we're going to get 8.99 times 10 to the 9th times 2 times 10 to the negative 4th times 3 times 10 to the negative 4th all over 5 meters squared. So, if you do the math for that and you do it right, it should come out to 21.57 newtons. Alright, and we can tell, because this is a positive and this is a negative, if we were to try and find what is the force and force and direction on this one, we would know that the magnitude is 21.57 and it is being attracted to this one. So it is 21.57 newtons to the left. Alright, now we're going to try another one. So it'll be very similar. Say we have another positive charge here, but a positive charge over here as well. Again, this is fixed, this one can't move. We're going to be calculating the force experienced and the direction of the force for this one. So, say this one is 7 times 10 to the negative 4th coulombs, and this one is 4 times 10 to the negative 4th coulombs. And this time let's say they're 10 meters apart. If we plug everything in just like we did before, I won't write it all out this time, but if you do the exact same thing, your force should come out to 25.17 newtons. Now, because these are both the same charge, we know that this one's fixed, it's not going anywhere, but it will repel this one, so it's going to be going to the right. Okay, I hope that made sense. We're going to go a little bit more in depth. I'm going to go ahead and erase this. We're going to try a sample problem similar to one that's on the homework. Almost exactly the same, actually. So, this is number 3. We're going to say we have 4 charges forming a perfect square with a side of 50 centimeters. And there's one charge in the middle. That should be right in the middle. The charges are going to be 2, -3, -4, 1, and 1.22. Okay, so this is looking like it's a lot, but let's remember, if we just remember that positives are going to push apart, these are the same, so they will push apart. So this is experiencing a push this way, and a push this way, a pull this way, and a pull this way. Now if we look at our equation again, we know that we don't, because the radius, or the r value is going to be the same on all of these because it's a perfect square, and the q values aren't squared, we can say that these will just cancel out. So instead of having a -3 in this direction, -4 in that direction, we can just say it's going to have a -1 in this direction. And same with this. Instead of having a 2 and a 1, we'll just say that there's a 1. So, I'm going to get rid of these. The forces that this is going to experience are going to have a net 1 in this direction and a net 1 in this direction. Again, because the r values are all the same, these are all equidistant, we know using trigonometry that the horizontal values of these vectors will be the same, but in opposite directions, so they will cancel. However, the downward vectors of both of them will both take effect. So we're going to have both of those. Now, in order to find all the variables we need, we already have Q1 and Q2 for these two different vectors. So if we plug those in, I'm just going to write the value for k again, 8.99 times 10 to the 9th times by the absolute value of 1.22. Oh, these are nanocoulombs. I apologize, I should have written that earlier. (1.22) times 10 to the negative 6th times 1 times 10 to the negative 6th, and absolute value. Now, the R value is a problem. We don't actually have this value right here, but we do know that it's 50 centimeters to a side. So we can remember that 25 centimeters halfway, 25 centimeters this way, Pythagorean theorem, and we'll get a value of 0.3536 meters for the R. So we'll square that. Now if you do all this math, you'll find that the force is equal to 0.1661 newtons. And that was for this vector right here. So we make another triangle, 0.1661. We know that this is 45 degrees. So if you take the cosine of 45 degrees and multiply it by 0.1661, you should get this value right here. And we find out that that value is 0.1175 newtons. Now, since we already solved for one of these downward vectors and we know they're the same, we don't have to solve for it again. So we just double that, and we get a value of the forces experienced will be 0.2349 newtons downwards. And that's our answer. I hope that was helpful. That's a brief explanation of Coulomb's law.